Lesson 9-6, Find Probabilities of Compound Events. So in this lesson, the difference between this and lesson 9-5 is that instead of just finding the number of outcomes that are possible, we're actually going to look at the probability of those outcomes occurring. Again, we're going back to that theoretical probability that you learned about in an earlier lesson. So take a look at the solve and discuss it. Talia is playing a game in which she must choose option 1 or option 2, and then spin the game wheel, flip the coin, and roll the number cube labeled 1 through 6. So she has two options. In order for her to win a prize, all the conditions under each chosen option must occur. Which option should Talia choose? So in this problem, what we're really looking for is which of those two options gives her the better chance of winning. I look at the spinner and I see a lot of different colors. I see a lot of different letters, although I do see that perhaps, no, maybe not. Maybe there's no repeats on there. But look at the spinner. How many sections are there on that spinner? Count them up. On this spinner, there are 15 separate sections that are all the same size. In this spinner, there are 15 equal size sections. So in option 1, it tells us the game wheel lands on S. So we have to go back to the spinner and determine how many sections are labeled S. In this case, there is only one, which means the probability of spinning the spinner and it landing on S is 1 out of 15. The second thing we need to look at in option 1 is the coin. The coin has two possible outcomes. If we want it to land on tails, as we do here, then we have a 1 out of 2 chance that it lands on tails. And then the third item in option 1 is the number cube, and they want us to roll an even number. Well, on a number cube there are 6 possible outcomes, and 3 of them are even numbers, 2, 4, and 6. So in order to find the probability of what would happen in option 1 if all 3 of these things were to occur, so just like in the last lesson where we looked at the total number of outcomes, which can be determined by multiplying the number of outcomes for each individual event, we can do the same thing here in order to determine the probability of option 1. So option 1 has a 3 out of 180 chances of all 3 of those events occurring in the same option, which is 1 out of 60. Now let's take a look over here at option 2. This time in option 2, we want the game wheel to land on Z. So again, I still have 15 sections, and I need to look at how many of them have Z as their label, and I only see 1 again. So that's a 1 out of 15 chance of the wheel landing on Z. Then I look at the second thing. The second thing I'm looking for is the coin, and it says the coin lands on either side. So in other words, it doesn't matter if I flip the coin or not, because if it's heads or tails, that's either side, then that outcome is favorable. So in this case, I have a 2 out of 2 chance of getting what I need for the coin. Then I have to look at the last thing, which is the number cube, and I want the probability that the number cube lands on a 3. Well, the number cube still has 6 sides, but the number 3 is only one of those 6 outcomes. So in option 2, when I multiply those 3 fractions together, I get 2 as my numerator, and in the denominator, I still get 180. Okay, the number of outcomes between the spinner, the coin, and the cube has not changed. What does change is the number of favorable outcomes, because it depends on what we want to have happen. So in this case, 2 out of 180 actually simplifies to 1 out of 90. So where do I have the greater chance? I have a greater chance if I choose option number 1. Now I want you to read carefully through example 1. Take a look at the 2 posters, the one that says flip to win and the one that says flip and spin. These are 2 different games from the school fair, and what Sadie is trying to determine is which game she should play. In other words, which game gives her the better chance of winning. You'll notice that there are 3 steps here, and in each step, a table is made to determine the number of outcomes and the number of favorable outcomes. So when we compare the probabilities of each game, we can determine which game gives her the better chance of winning. Once you've finished with looking through example 1 and reading carefully through those 3 steps, go down to the try it at the bottom of the page and try that one. Come back to the video when you're ready to check your answer. All right, did you try it? Did you look carefully? This time the spinner is different than it is in the flip and spin game up in example 1. So what we're trying to do is determine how the new spinner changes the probability of winning a prize. Even though the spinner is changed, we're still looking at the game flip and spin, which means we're still looking at the same way that we can win that game. Remember, the flip and spin game is a winning game when you spin blue and flip heads. So in this case, we have changed the spinner, and the spinner is now a 5-section spinner instead of a 4-section spinner. But the probability of winning a prize now is 1 out of 5. We still have the same chances on the coin, though. If we want to flip heads, we still have one outcome that's heads out of the 2 possible outcomes on the coin. So right now, if we were to spin the spinner and flip the coin, we have a 1 out of 5 chance of spinning blue. That's this section. And we have a 1 out of 2 chance of flipping heads on that same combination. So now as we look at how we can win a prize in this game, we need to put these 2 fractions together by multiplication. Using the 5-section spinner, the probability of winning a prize is now 1 out of 10, or just 10%. When you look back up at the top, the probability of winning a prize at flip and spin is only 12 5/10%. But that's greater than the 10% if we change that spinner. So in this case, it is less likely that a player will win a prize when using the 5-section spinner than when using the 4-section spinner. In other words, the more outcomes you have, the fewer chances you have of winning. In example 2, we're going to use a tree diagram and flipping a penny, or flipping another coin 3 times, and determine the probability that when the coin is flipped 3 times, it will land heads up exactly 2 times. Since flipping a coin produces 2 possible outcomes, heads or tails, each time it is flipped, you can use this tree diagram to trace and look for all the places where exactly 2 heads have occurred. Remember that when you flip that coin once, twice, 3 times, and each outcome that's possible is 2 for each flip, you have a total of 8 possible outcomes. 3 of these outcomes are favorable, meaning they match the description of what we want to have happen, and that is exactly 2 heads out of the 3 flips. So a probability of 3 out of 8 is the same as 37 5/10%. Now the try it question asks us about this same tree diagram. It asks us if it's more likely that a coin flipped 3 times will land heads up exactly once or heads up exactly twice. Notice that there's a typo there. We don't need the number when they use the word twice. Pet peeve of mine. Okay, so let's go back to the problem. So we already know that if it's going to land heads up exactly 2 times, okay, that's a 3 out of 8 probability. That's this piece right here from our example. So what we really need to look at is how many chances does it have to land on heads exactly once? In other words, go back to your tree diagram and find all the places where it just lands on heads 1 time. I see it here, and here, and here. And if you look there, that's 3 outcomes out of 8 possible. My pen's not working. Oh, that was bad. Hold on. Okay, that's better. So what do you notice? You should notice that those 2 fractions or percentages are identical. because 3/8 is still 37 5/10%, regardless of if we're looking at exactly once or exactly twice. Okay, in example 3, this one gets a little complicated. So they use an organized list to show all the possible outcomes that can happen when two students are selected to receive baseball tickets. Okay, so in this case, it doesn't matter which student is picked first and which student is picked second. Okay, but that's how they've got it organized. So we can see if we have included all the possible outcomes. The problem, though, asks us, what is the probability that Mark's name will be drawn to win one of the two tickets? So what we see here is everywhere that Mark is in the drawing for one of those two tickets is a positive or favorable outcome. And I see that Mark could be chosen with Angie, Carly, Phil, and Josie. So those are 4 outcomes right there. But that's if Mark is picked for the second ticket and Angie, Carly, Phil, or Josie are picked for the first ticket. But if Mark is picked for the first ticket, like that right here, then all 4 of these outcomes include him as one of the winners, which means there are 8 favorable outcomes out of the 20 possible outcomes, which is 40%. Now let's take a look at the try it question. Does Mark have a greater chance than Carly of winning the tickets? Explain using probability. So when we go back through the list here, Carly is listed in several places as a winner, one of the winners. And if you'll notice here, she is also listed 8 times out of the 20 possible outcomes, which means her chances of winning are still 40%. So neither of them has a greater chance. In fact, they have the same chance. Okay, so you can see Carly, 1, 2, 3, 4 places on the individual list. And then here's Carly listed 4 times as the first ticket winner. Now let's try a few problems together. Take a look at number 4. One of 3 contestants will be randomly selected to win a prize. One of the 3 different prizes will be randomly awarded to the contestant whose name is selected to win. The tree diagram shows all the possible outcomes of this contest. So what they don't show you is what the final outcome is, but if you trace the tree diagram, you can find that information. For example, if Pedro is the winner, he could win prize 1, Pedro could win prize 2, or Pedro could win prize 3. If Whitney is the winner, Whitney can win prize 1, Whitney can win prize 2, or Whitney can win prize 3. And if Brian is the winner, Brian could win prize 1, Brian can win prize 2, or Brian can win prize 3. So when they ask us what is the probability that Whitney will win prize 2, there is only one outcome out of all of them that shows Whitney winning prize number 2. Now, how many outcomes are there altogether? Well, if you count them up, there are 9. So the probability that Whitney will win prize 2 is 1 out of 9. Now let's take a look at question 5. The table shows all the possible outcomes for flipping a coin and spinning the pointer of a spinner with 4 equal-sized sections labeled 1 through 4. The coin can either land on heads or tails. It only has 2 options. The spinner has 4 options, and each of those are numbered 1, 2, 3, or 4. So part A says, what is the probability that the pointer will stop on 3 and the coin will land on heads? So we're looking for that combination to show up, and it's right here. So the probability that it lands on 3 and heads is 1 out of the total number of outcomes, which is 8. B, what is the probability that the pointer will stop on an odd number and the coin will land on heads? So this time we have to be a little bit more creative. The odd number means that the number is either a 1 or a 3. And heads means that it's a heads, not a tails. So when I look at my diagram here, my chart, I have heads with 1 and I have heads with 3. So there are actually 2 options where it is an odd number and heads out of the 8 possible outcomes, which is the same as 1 out of 4. Now let's try number 6. I'm going to go back to my black pen. There we go. Okay. A fair coin is tossed twice in succession. That means 2 times in a row. The sample space is shown where H represents heads up and T represents tails up. Find the probability of getting exactly 1 tail. So there are 4 total outcomes here. 2 heads, 2 tails, or 1 heads and 1 tails. Okay, how many outcomes have exactly 1 tail? And I need to change this because there are 4 outcomes total here. But out of those 4 outcomes, how many of them have exactly 1 tail? And that is 2 of those outcomes. There are 4 possible outcomes, which are equally likely. So getting tails is a 2 out of 4. Okay, which is the same as 1/2 or 50%. Now take a look at number 7. We have another tree diagram here, and it shows the sample space of 2-digit numbers that can be created using the digits 2, 6, 7, and 9. What is the probability of choosing a number from the sample space that contains both a 9 and a 6? So we need to look at all the possible outcomes in the list. And here's where I want you to take a look. So in the first tree, you start with a 2, and it branches out to a 6, a 7, and a 9 right here. Okay? These 3. So you have 26, 27, and 29. Then when you go to the next number, the 6, it also branches out into a 2, 7, and 9, meaning the numbers are 62, 67, and 69. As we progress, we get a 7 with a 2, which is 72, a 7 with a 6, which is 76, and a 7 with a 9, which is 79. And then last but not least, when we start with a 9 and we end with a 2 or a 6 or a 7, we can see that we have a total of 12 possible outcomes. There are 3 for each of those numbers as the starting number. So how many outcomes include both a 9 and a 6? So this is where we go back through the list and we're looking for 9 and 6 together. So I see this outcome right here, and I see this outcome right here. Did I miss any? Are there any other outcomes that have both a 6 and a 9? I don't think so. I think there are only 2 outcomes out of the 12, and I want you to figure out what percent that is. Remember that you divide 2 divided by 12, and then do times 100 to get your percent. And that equals about 17%. Now I'd like for you to try the work on your own.